A planet can be stretched into a long stream of gas before being swallowed whole. This is the violent reality of a black hole's tidal disruption. By the end of this journey, you will understand the precise physics that tears worlds apart and what these events reveal about the nature of space and time. We will uncover how a planet's final moments create a brilliant flash of light visible across the cosmos, and why some debris escapes this gravitational monster entirely. How do you picture the end of a world? At the heart of this destructive power lies a point of infinite density, a singularity. This is the black hole's core, where all the matter it has ever consumed is crushed into a volume smaller than a single atom. Surrounding this unfathomable point is the event horizon, the point of no return. Think of it not as a solid surface, but as an invisible threshold in space. Once anything, a planet, a star, or even a beam of light, crosses this boundary, it can never come back. The gravitational pull becomes absolutely inescapable. Black holes themselves come in different classes, but the true planetary destroyers are the supermassive ones. These are not the remnants of dead stars, but colossal beasts that sit at the center of most galaxies, including our own Milky Way. They contain the mass of millions, even billions of suns, all compressed into a region of space that could fit within our solar system. It is the staggering gravitational field of a supermassive black hole that warps the very fabric of the universe around it, creating the conditions for a planet to be torn apart long before it ever reaches the event horizon. This warping of spacetime is the key to understanding the violence that follows. This stretching force is a difference in gravity so extreme it can pull a world apart from itself. The same fundamental physics governs the ocean tides on Earth, where the moon's gravity pulls more strongly on the side of our planet facing it. But near a black hole, this gentle tug becomes a cosmic executioner. The difference in gravitational pull between one side of a planet and the other becomes unimaginably powerful. It is this imbalance, this tidal force, that does the tearing. Think of a planet made of rock and metal held together by its own gravity. As it drifts closer to the black hole, the side facing the monster feels a ferocious pull forward, while the far side feels a weaker pull. The entire world is stretched, elongated, and squeezed all at once. This violent process even has a vivid name, spaghettification, because the planet is stretched into a long, thin stream of matter, like a strand of spaghetti. For this to happen, the tidal force must overcome the planet's gravitational binding energy, the very glue that holds it together. The rock and metal that form mountains and core are simply not strong enough to resist. They surrender to the pull and the world is torn asunder. The point of no return for this destruction is not the event horizon, but a specific distance farther out known as the tidal disruption radius. It is at this precise boundary where the black hole's stretching power exceeds the planet's own gravity. This is the moment of truth, the instant a solid world ceases to be. So what determines this critical distance? The fate of a planet hinges on a simple, brutal calculation. This critical distance, the tidal disruption radius, has a formal name in astrophysics, the Roche limit. It is the precise boundary where a celestial body's self-gravity is overpowered by the tidal forces of a much more massive object. For a planet and a black hole, the Roche limit is not a fixed number. It is a unique calculation for every single pairing, a cosmic equation that determines survival or annihilation. The formula itself hinges on two key factors, the density of the planet and the mass of the black hole. The distance at which a planet is torn apart is roughly proportional to the black hole's mass raised to the 1/3 power. multiplied by the ratio of the black hole's density to the planet's density, also raised to the 1/3 power. While that may sound complex, the underlying principle is beautifully simple. A dense, compact planet, like a solid ball of iron, has a stronger gravitational hold on itself. It can therefore venture a little closer to the brink before the black hole's tidal forces win the tug-of-war. In contrast, a gas giant like Jupiter, a vast and less dense world, is far more vulnerable. It would be shredded at a much greater distance from the same black hole. For a supermassive black hole, this disruption radius lies far outside the event horizon. A planet does not need to cross the point of no return to be destroyed. Its doom is sealed thousands, even millions of kilometers away, long before it could ever be swallowed whole. Astronomers use these calculations to model these violent encounters, predicting the brilliant flashes of light that signal a world's end. The specific properties of the planet and the monster it encounters write the entire script for this cosmic drama. Now we can witness the first stage of this destruction, the initial approach. The planet's fatal journey begins not with a direct plunge, but with a nudge. In the chaotic core of a galaxy crowded with stars and planets, a gravitational kick from a passing star can send a world spiraling inward. Its once stable orbit is perturbed, setting it on a new, doomed trajectory straight toward the supermassive black hole. Drawn in by the immense gravity, the planet begins to accelerate, falling faster and faster as the darkness grows. From a distant observer's perspective, the planet still seems to be following a predictable path. But this is an illusion. The extreme gravity warps the very rules of reality. A clock on the planet's surface would now tick slower than one far away, a bizarre effect known as time dilation. The planet itself is no longer a perfect sphere. The black hole's pull stretches it, creating a subtle elongation, a slight egg shape pointing toward the gravitational monster. This is the calm before the storm. The planet remains whole, but it is screaming under the strain. Immense tidal forces are not just reshaping it from the outside, they are cooking it from within. The constant stretching and squeezing generates intense friction, a process called tidal heating. This could trigger global volcanic eruptions on a scale never seen before, with continents cracking and molten rock bursting through the crust. The world is being physically stressed to its breaking point, racing toward the moment its own gravity can no longer hold it together. The planet's crust shatters first. As it crosses that invisible boundary, the tidal disruption radius, the world can no longer hold itself together. The difference in gravitational pull between the side facing the black hole and the far side becomes greater than the planet's own gravitational self-attraction. It is a battle of forces, and the planet's own gravity has just lost. Global fault lines rip across the surface in an instant, a network of fractures so vast the entire world cracks open like an egg. The solid ground we stand on is simply not strong enough. Then the deeper layers succumb. The planet's mantle and core are subjected to the same extreme stretching. The entire world, from its metallic heart to its fractured surface, is pulled into a long, thin stream of superheated material. This is spaghettification in its raw, violent reality. The transformation from a spherical world to a linear stream of debris is breathtakingly fast. For a planet like our own Earth falling toward a supermassive black hole, this entire disruption could be over in mere minutes, perhaps even seconds. This is not a slow unraveling, but a catastrophic and instantaneous reordering of matter. The energy released in this self-destruction is staggering, converting the planet's mass into an intense flash of heat and light. The world is effectively being shredded back into its constituent atoms, a cloud of primordial gas and dust. This violent death, however, is not the end of the story. The debris from the shattered planet does not simply vanish. It forms the raw material for the next act in this cosmic drama, the birth of a brilliant and destructive structure known as an accretion disk. This transformation into a cosmic filament is a brutal physics experiment. The planet becomes a test subject for the gradient of the gravitational field. Think of gravity not as a single, uniform force, but as a steep slope. Near the black hole, the slope is so incredibly steep that the pull on the planet's leading edge is vastly stronger than the pull on its trailing edge. The front is being yanked forward at a far greater acceleration than the back, stretching the entire world lengthwise. At the exact same time, the sides of the planet are being squeezed inward, as if caught in a cosmic vice. This combination of radical stretching and lateral compression is what forges the spaghetti-like shape, elongating the world into a thin, hot stream of matter. This is not a gentle pulling apart. The forces at work are so immense they overwhelm the very bonds holding the planet's molecules together. Solid rock shatters into dust. Metallic cores are torn asunder. The planet's own internal energy, the heat trapped deep within for billions of years, is violently liberated in an instant. This is gravity, the force that gives planets their shape, taken to its most destructive extreme. It systematically dismantles a world, reducing it to its most basic components. And this stream of debris, born from such violence, now begins its final, luminous dance. This stream of planetary debris now faces its ultimate judge, the event horizon. While the planet was torn apart far outside this boundary, the horizon dictates the final fate of every single atom. It is a one-way street in the fabric of the universe. Any piece of the shattered world that crosses this invisible line is gone forever, its mass and energy added to the black hole, but the journey does not end neatly. The debris cloud is a chaotic mess, and each fragment has its own trajectory. Much of this material, possessing a significant amount of sideways motion from the planet's original orbit, simply cannot fall straight down. Think of a satellite in a stable orbit around Earth. It is constantly falling toward the planet, but its tremendous sideways velocity means it keeps missing. The same principle applies here, but with far higher stakes. A large portion of the shredded planet will miss the event horizon on its first pass, its angular momentum slingshotting it back out into space, only to be pulled back in by the immense gravity. This material does not escape. Instead, it is captured, destined to orbit the monster that destroyed its home. The event horizon itself is not a physical barrier you could touch. For a supermassive black hole, it is an immense sphere in space, a region so large it could easily swallow our sun and all the planets. It acts as a cosmic drain, a final sink for matter. The interaction between the speeding debris and this ultimate boundary creates a complex and violent ballet, sorting the material into two distinct groups. One stream is doomed to immediate consumption, vanishing from our universe in silence. The other is granted a temporary reprieve, forced into a swirling, frenzied orbit. And it is from this second group that a spectacular and destructive light show is born. This chaotic debris cloud is the raw material for a cosmic engine. The pieces of the shattered planet that missed their immediate appointment with the event horizon are now trapped in wildly elliptical orbits, but this is not a stable system. With countless fragments all moving at different speeds and directions, collisions are inevitable. Every time two pieces of debris smash into each other, they lose a little bit of their orbital energy, their angular momentum. Think of it as a form of friction in the vacuum of space. This constant bumping and grinding acts as a brake, slowly robbing the material of its ability to stay in a wide orbit. Instead of continuing to circle the black hole at a safe distance, the entire cloud of gas, dust, and plasma begins a slow, inevitable spiral inward. This vast, swirling whirlpool of superheated matter is what astronomers call an accretion disk. It is not a solid ring like Saturn's, but a frenzied, chaotic swarm of particles, all racing around the gravitational drain. As this material is pulled closer and closer to the event horizon, something remarkable happens. The immense gravitational forces compress it, packing the atoms together with unbelievable pressure. This compression generates intense heat through friction, cooking the disk to temperatures that can reach millions of degrees. At such extremes, the entire disk begins to radiate, glowing with a ferocious light that spans the entire electromagnetic spectrum. It shines in radio waves, visible light, and powerful X-rays, transforming the black hole's vicinity from a dark abyss into one of the brightest spots in the galaxy. This brilliant flare is the primary way we detect these events across cosmic distances. The death of a single planet provides the fuel for a transient beacon, a final shout of light before the material is consumed by the silence within. The environment inside this glowing disk is a realm of extreme physics where matter is pushed to its absolute limits. This superheated disk glows with the fury of a newborn star. The intense friction and pressure within the swirling debris raise its temperature to millions of degrees, and like a piece of iron pulled from a forge, it begins to radiate. This is thermal emission, the fundamental process by which hot matter releases its energy as light. The result is a flare of radiation so brilliant it can, for a few fleeting weeks, outshine every single star in its host galaxy combined. This is the final, luminous cry of a destroyed world. Astronomers carefully track this light, plotting its intensity over time to create what is known as a light curve. The story it tells is unmistakable. The brightness surges rapidly to a sharp peak as the bulk of the planetary debris falls inward and forms the dense, hot disk. Then, as the black hole steadily consumes this fuel, the light begins a long, slow fade. We do not observe this death throe with just one kind of eye. Our optical and ultraviolet telescopes capture the fierce white-hot glow of the outer disk, while our X-ray observatories peer into the inner sanctum, where temperatures soar to tens of millions of degrees. It is this combination of signals across the entire spectrum of light that confirms the event. A sudden spike in visible light alone could be a supernova. A burst of X-rays might be something else, but when we see the characteristic light curve appear simultaneously in optical, ultraviolet, and X-ray data, we know we are witnessing a planet being consumed. The death of a single world becomes a temporary beacon, illuminating the presence of a hidden monster. But how do we spot these fleeting cosmic fireworks in the vast darkness of space? This brilliant flare of light is our only signal from such a distant catastrophe, a cosmic telegram announcing a world's end. But how do we, from our small planet, even begin to spot these brief, brilliant flashes in an ocean of darkness? The answer lies in a new generation of cosmic sentinels, automated sky surveys that never sleep, projects like the Zwicky Transient Facility in California and the soon-to-be operational Vera C. Rubin Observatory in Chile are designed for this very purpose. These are not telescopes that stare at one single star. Instead, they act as giant mechanical eyes, repeatedly scanning vast swaths of the heavens night after night. Their sole mission is to detect change, to find anything that moves, flickers, or suddenly brightens. When a new point of light flares into existence where there was only darkness before, especially in the core of a distant galaxy, it sets off a digital alarm for astronomers worldwide. This is the first clue, a single line in a much larger story. A sudden bright spot in a galactic center is a strong hint, but it is not yet proof. The light must be interrogated. The next critical step involves a global call to arms. Other, more specialized telescopes are swiftly pointed at the coordinates of the alert. These instruments perform a kind of cosmic forensics, breaking the light down into its constituent colors to create a spectrum. This rainbow holds the event's deepest secrets. By analyzing the specific fingerprints of elements within this light, scientists can determine the very composition of the material being devoured. If they detect strong signals from silicon, oxygen, and iron, it paints a vivid picture. These are the building blocks of rock and metal, the unmistakable chemical signature of a terrestrial, Earth-like world being shredded back into its elemental parts. The spectrum also reveals motion through the Doppler shift. The light from gas swirling at incredible speeds in the accretion disk is stretched and squeezed, its colors shifting subtly. By measuring this shift, astronomers can clock the velocity of the orbiting debris. This speed, in a beautiful application of Newton's laws, allows them to calculate the mass of the invisible monster at the center, the supermassive black hole itself. Each tidal disruption event is a rare and precious data point. They do not happen often in any single galaxy, which makes every successful detection a triumph. The combined data from these observations, the light curve, the elemental composition, and the velocity measurements, all weave together to form a complete and vivid portrait of the event. We can almost see it, a world of rock and iron stretched into a stream, its atoms glowing with ferocious heat as they spiral into the dark. This distinction between star and planet is written in the light itself. The death of a star is a far grander, more explosive spectacle. Because a star is so much larger and more massive than any planet, its tidal disruption radius lies much farther out from the black hole. The monster can begin tearing the star apart from a greater distance, but the true difference lies in what holds these objects together. A planet is a relatively simple structure, bound into a sphere by its own gravity. Overcome that self-attraction and the world comes apart. A star, however, is a titanic balancing act. Its immense gravity is constantly trying to crush it, but this force is counteracted by the tremendous outward pressure from nuclear fusion in its core. When a black hole disrupts a star, it is not just overcoming gravity, it is dismantling a functioning nuclear reactor. The result is a far more violent and luminous explosion. The sheer amount of fuel available is staggering. A single star contains enough gas to create an accretion disk that can shine with the power of 1 billion suns for months or even years. The light curve from such an event is a brilliant, long-lasting beacon. In contrast, the disruption of a planet like Earth would produce a flare that is thousands of times fainter, a brief, hot flash that fades in a matter of weeks. The chemical signature in the light is also a dead giveaway. The spectrum from a shredded star is dominated by the simple, lightweight elements of hydrogen and helium, the primary components of suns. A disrupted planet, however, tells a more complex story. Its light would bear the unmistakable fingerprints of heavier elements, the silicon, oxygen, and iron that form the bedrock of terrestrial worlds. This is how we know what we are seeing. Spotting a planetary disruption is a monumental challenge precisely because it is so faint and fast. Yet there is a fascinating paradox at play. While a stellar disruption is easier to see, a planetary one might be far more common in the chaotic core of a galaxy. Planets vastly outnumber stars. They are the smaller, more numerous pebbles in the cosmic stream, and they are far more easily gravitationally kicked onto a fatal trajectory. Every flicker of light we detect from a galactic center is a puzzle. Is it the final, grand performance of a star or the quieter, more subtle end of a world? By carefully reading the clues in the light, its brightness, its duration, and its elemental composition, astronomers can perform this cosmic autopsy. They can determine not just that a black hole is feeding, but what it is eating. This forensic ability transforms a single flash from a mere curiosity into a critical data point. It helps us map the population of invisible black holes and understand the violent ecology of the galactic centers they rule. But the black hole itself is not a static monster. It can spin, and this rotation transforms the entire destruction process. A spinning black hole, a cosmic whirlpool of unimaginable scale, does not just pull on matter. It drags the very fabric of spacetime around with it, a phenomenon predicted by Einstein's general relativity known as frame dragging. The space near the black hole is no longer a stationary stage but a rushing river flowing in the direction of the spin. This creates a region just outside the event horizon called the ergosphere, where nothing can stand still. Every object caught here is forced to move, swept along in the current of twisted spacetime. For a doomed planet on its final approach, this spin introduces a critical new variable. The outcome now depends on the planet's direction of travel relative to the black hole's rotation. Imagine a planet falling in, orbiting in the same direction as the black hole spins. This is a prograde encounter. Here, the planet is essentially moving with the flow of spacetime. This cooperative motion gives it a little more stability, allowing it to venture slightly closer to the event horizon before the tidal forces finally overwhelm it and tear it apart. The disruption happens deeper within the black hole's gravitational well. Now, picture the opposite scenario, a retrograde encounter. The planet is moving against the spin, fighting the current of spacetime. In this hostile approach, the effective gravitational forces it experiences are stronger. The planet is ripped to shreds at a much greater distance from the event horizon, denied even the chance to get close. This directional bias means that for the exact same black hole and the exact same type of planet, the point of destruction is not a fixed location in space. It is a shifting boundary determined by the geometry of the encounter. This spin also supercharges the aftermath. The debris from the shattered planet, now caught in the swirling ergosphere, is whipped into an even more frenzied and compact accretion disk. The frame-dragging effect forces the material into tighter, faster orbits, dramatically increasing the friction and compression. This more efficient conversion of mass into energy can produce a significantly brighter and hotter flare of radiation. The death cry of the planet is amplified by the black hole's own rotation. This is why no two tidal disruption events are ever truly identical. The mass of the black hole, the density of the planet, and now its spin and the angle of approach all combine to write a unique script for each cosmic demolition. The spin is a fundamental signature of the black hole, a hidden property that reveals itself only through the violent death of whatever falls into its grasp. These cosmic demolitions are recreated not in a laboratory, but inside the memory of supercomputers. Since we cannot witness a planet's destruction up close, scientists build virtual universes governed entirely by the unbreakable laws of physics. They write complex code that embodies Einstein's general relativity and the rules of fluid motion, then set a digital planet on a collision course with a digital black hole. The simulation tracks the fate of millions, sometimes billions, of individual particles, each one representing a piece of the doomed world. Every single particle feels the pull of gravity, the stretching tidal force, and the collisions with its neighbors. The calculations are so immense that only the most powerful supercomputers on Earth can handle them, running for weeks to simulate events that last mere minutes in reality. This virtual experimentation reveals secrets we could never see with our telescopes. We can watch the internal stresses build within the planet's mantle, seeing exactly where the first cracks will form. We can observe the chaotic whirlpool of the accretion disk as it first ignites, tracing the flow of energy from the inner edge to the outer rim. These models allow scientists to play with the variables of destruction. What happens if a dense, iron-rich planet takes a grazing path past the black hole? The simulation shows it might be only partially stripped, its outer layers torn away while its solid core survives, flung back into the darkness as a scorched, wandering remnant. What if a gaseous world makes a direct plunge? The model reveals it could be completely vaporized, its matter spread into a thin, hot haze almost instantly. Every parameter, from the black hole's immense mass to the precise angle of the planet's approach, writes a different ending to the story. These are not just animations, they are rigorous numerical experiments. The insights they provide are the critical link between the brilliant flash of light we observe and the violent physical reality that caused it. They breathe life into theory, allowing us to witness the invisible and understand the fate of worlds from the safety of a computer screen. The violent physics that tears a planet apart began as lines on a blackboard. Albert Einstein's theory of general relativity, published in the early 20th century, gave us the mathematical language to describe gravity not as a simple force, but as the warping of spacetime itself. From this new understanding, a startling possibility emerged. It took decades for that possibility to take a precise form. In the 1970s, theorists formally proposed that a black hole's immense tidal gravity could shred a passing star. The idea was revolutionary, but for a long time it remained just that, an idea. The universe had not yet provided a clear example. The first strong candidate for a stellar tidal disruption event was not identified until the 1990s. This discovery was not made with visible light, but with the invisible energy of X-rays and ultraviolet radiation, wavelengths where the ferocious heat of a newborn accretion disk screams into the void. Our telescopes had finally caught up with our theories. Since that first detection, dozens of candidate events have been added to the ledger, yet a confirmed planetary disruption remains one of the field's holy grails. The flash from a dying world is simply so faint and so fast that it slips through our nets. The true explosion in this field has happened in just the last 10 years. A new era of wide-field optical surveys began scanning the skies, not once a year but every single night. These relentless digital eyes catch the subtle flickers that older telescopes would miss. Each new flash is a data point that refines our virtual models, and many have brought stunning surprises. Some tidal disruption events do more than just glow. They channel immense power into narrow jets of plasma, firing material away from the black hole at nearly the speed of light. The history of this research is a powerful testament to how science truly works. It is a slow, deliberate dance between prediction and observation. A concept born from pure thought is gradually, painstakingly confirmed by the cold, hard light from the depths of space. This entire journey, from Einstein's equations to the automated alerts of a modern observatory, underscores a profound truth about our universe. The most violent secrets are often hidden in the faintest, most fleeting whispers of light. So what becomes of the planet's shattered remains? The debris follows a cosmic sorting process, a gravitational triage that dictates three distinct and permanent fates. A surprising amount of the material, roughly half in many simulations, is given a violent pardon. This debris is flung outward with such immense speed that it completely escapes the black hole's gravitational grasp. It sails away on hyperbolic orbits, never to return. These scattered atoms, the ghostly remnants of mountains, oceans, and a metallic core, are now condemned to an eternity of lonely travel through the interstellar void. They become unbound nomads, silent testimonies to a world that no longer exists. The remaining half of the debris is not so lucky. This material is captured, bound to the black hole by gravity's unbreakable chains. But its consumption is not immediate. The long, thin stream of gas must first settle into a stable orbit. This process, called circularization, is a chaotic and gradual ballet. The stream wraps around the black hole, but because of relativistic effects, the orbits of individual particles precess or wobble like a spinning top slowing down. Different parts of the stream collide with each other at ferocious speeds, robbing each other of energy through this violent friction. It is this self-interaction that slowly transforms the chaotic stream into a smooth, swirling whirlpool, the accretion disk. Once the disk forms, the final spiral begins. The material does not fall straight in. It is caught in a slow, inevitable drain, governed by the viscosity of the superheated gas. Think of this as the internal friction of the disk itself. This viscosity works to transport angular momentum, the property that keeps things in orbit outward. As momentum shifts to the outer disk, the inner material is free to drift closer to the abyss. This is a slow death march, taking anywhere from weeks to months. The innermost material finally reaches the precipice, crossing the event horizon and vanishing forever. Its mass is added to the black hole, making the monster infinitesimally more massive. In its final moments, a tiny fraction of this doomed matter achieves a strange kind of immortality. As the gas is compressed and heated to millions of degrees in the inner disk, a small percentage of its mass is converted directly into energy, powering the brilliant flare we observe. This is the ultimate transformation of a world. The planet is dismantled and redistributed across the cosmos. Part is ejected as wandering ghosts, part is radiated away as a final shout of light, and the rest is consumed by the silence. The entire existence of a world is rewritten into these three simple lines of cosmic destiny. The same light that signals a world's end also illuminates its beginning. These violent encounters reveal a profound truth about planet formation, that it is an incredibly robust and universal process. We once assumed planets could only coalesce in the quiet, safe suburbs of a galaxy, far from the chaotic core. The very presence of planets near a supermassive black hole shatters that assumption. It means that the basic recipe for building worlds, the slow accumulation of dust and gas around a young star, can succeed even in an environment of intense radiation and ferocious gravitational tides. Planet formation is not a delicate flower that wilts under pressure. It is a hardy weed that can grow in the most unforgiving cracks of the cosmos. When we detect the flash from a tidal disruption, we are not just watching a death, we are witnessing proof of life, or at least proof of a world's stubborn formation against all odds. The debris from that world becomes a direct sample, a message in a bottle composed of pure light. By analyzing the spectrum of the accretion disk's flare, astronomers can perform a kind of remote planetary geology. The specific wavelengths of light absorbed or emitted act as chemical fingerprints. Finding the signature of water vapor would be a stunning discovery, suggesting that icy worlds can form or migrate into these hostile zones. Detecting the spectral lines of silicates and metals would confirm the existence of terrestrial, rocky planets like our own, orbiting stars in the heart of the galactic storm. This is how we take the pulse of a planet we will never see, learning its composition from the very fire of its destruction. The existence of these doomed worlds also forces us to ask how they got so close to the edge. Their precarious orbits are a puzzle. They likely did not form in the shadow of the monster. Instead, they were probably born in safer, more distant orbits around their parent stars. A gravitational kick from a passing star or a close encounter with another planet could have sent them spiraling inward, a cosmic game of pinball that ended in catastrophe. This dynamic process of planetary scattering means the inner sanctum of a galaxy might be continuously supplied with fresh worlds to consume. Every tidal disruption event we observe is therefore a data point in a much larger census. It helps us map the hidden population of planets in galactic centers, telling us how common they are and what kinds of worlds can survive there. The death of a single planet connects its violent end directly back to its quiet birth, offering a unique and tragic window into the full life cycle of worlds across the galaxy. There is a theoretical boundary where even this cosmic violence is silenced. As we push the laws of physics to their absolute limits, we encounter a strange paradox involving the most massive black holes in the universe. Consider a black hole with a mass of billions, even tens of billions of suns. Its event horizon is so unfathomably large that it encompasses the very point where tidal forces should rip a planet apart. For any world falling toward such a leviathan, the tidal disruption radius lies inside the event horizon itself. The planet would cross the point of no return completely intact, swallowed whole before the stretching forces could ever begin their work. From our perspective in the outside universe, there would be no brilliant flare of light, no final shout of radiation. The world would simply vanish, its destruction hidden behind a curtain of absolute darkness. This bizarre scenario actually sets a firm upper mass limit for black holes that can produce the observable flashes we hunt for. The most colossal monsters in the cosmos feed in perfect silence. On the opposite end of the scale lies another exotic possibility, the realm of the incredibly small. Primordial black holes are hypothetical remnants of the Big Bang, some no larger than a single atom yet containing the mass of a mountain. A close encounter with such a tiny, unimaginably dense object would be a very different kind of disaster. It would not envelop and stretch a planet. Instead, it would punch a clean, microscopic hole straight through the world's core, exiting the other side like a cosmic bullet. The planet might survive the puncture, left with a perfectly bored tunnel through its mantle and crust, its structural integrity shaken but not completely broken. This is not spaghettification, but a precise and terrifying piercing. These thought experiments force us to confront the deepest questions in physics, questions about what truly happens to the information that defines a planet. According to the classical rules of general relativity, all the information about that world, every detail of its composition and history, is lost forever when it crosses the event horizon. But quantum gravity, our best attempt to unite the very large with the very small, suggests a different fate. It proposes that information cannot be truly destroyed. The quantum information that made up the planet, the specific arrangement of all its atoms, might not vanish. It could be preserved in some scrambled form on the event horizon's surface, or slowly leaked back out over eons through Hawking radiation. The ultimate fate of a consumed world, then, becomes a question that transcends gravity itself, touching on the fundamental nature of reality. These are not just abstract puzzles. They are the frontiers where our current understanding of the universe begins to fray, reminding us that even the most violent and well-studied cosmic events are gateways to mysteries we have only just begun to unravel. Alongside the brilliant flash of light, the destruction of a planet might also create a subtle tremor in the cosmos itself. These are gravitational waves, ripples in the very fabric of spacetime that travel outward at the speed of light. They are generated by any mass that accelerates, but to create a wave we can even hope to detect, the acceleration must be unimaginably violent and asymmetric. The process of a planet being stretched into a stream of debris fits that description perfectly. For a brief, chaotic moment, a tremendous amount of mass is being whipped around at a significant fraction of light speed. This is not a smooth, symmetrical collapse. It is a lopsided, catastrophic rearrangement of matter, and that kind of motion can literally shake the universe, sending faint whispers of gravity across interstellar space. Yet, for all their cosmic significance, these waves from a single planet would be incredibly weak. Our current gravitational wave observatories, like LIGO and Virgo, are masterfully tuned to listen for the collisions of stellar mass black holes and neutron stars, events that shake spacetime with a much deeper, higher frequency rumble. The death cry of a planet would be a far higher pitched and fainter chirp, lost in the background noise of the cosmos. The true revolution in listening for these events lies in the future, with a new kind of observatory built not on Earth but in the quiet vacuum of space. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will open an entirely new auditory range. It will consist of 3 spacecraft flying in a giant triangular formation millions of kilometers apart, using lasers to detect the subtle stretching of space itself. LISA is designed to be exquisitely sensitive to the lower frequency gravitational waves that current ground-based detectors cannot hear. This is the precise range where we would expect to hear the final, spiraling duet of a planet and a supermassive black hole. It would capture the in-spiral, the last few orbits before the world is torn asunder. Capturing both the light and the gravitational waves from the same event would be a scientific triumph of unparalleled value. The electromagnetic flare tells us what the debris is made of and how hot it is, painting a picture in color and heat. The gravitational wave signal would provide an independent and precise measurement of the masses involved, the spin of the black hole, and the exact dynamics of the orbit. It is like seeing a lightning strike and hearing the thunder. The light shows you the flash, but the sound tells you how far away it was and how powerful the bolt truly was. This multi-messenger approach would allow us to study the same cataclysm through 2 completely different senses, confirming our models with a clarity we have never before achieved. We would not just see the planet's death, we would hear the very spacetime around it ring like a bell. Our own existence is a direct result of this cosmic violence being kept at a distance. The universe operates on a simple, brutal rule. The conditions we observe must be compatible with our presence as observers. This is the essence of the Anthropic principle. We do not live on a world spiraling into a supermassive black hole, because such a place could never give rise to beings who could ponder its existence. The very fact that you are here to listen to this story is proof that our planet occupies a safe and stable orbit, far from the galaxy's chaotic core. Our solar system is situated in a quiet suburban arm of the Milky Way, a staggering 26,000 light-years from Sagittarius, a star, the supermassive black hole at our galaxy's center. This immense buffer of space and relative calm was not a mere convenience. It was an absolute prerequisite for life to emerge, evolve, and persist over billions of years. In the densely packed stellar cities of galactic centers, where stars and planets brush past each other, gravitational encounters are frequent and violent. A single close pass could easily kick a terrestrial world out of its safe orbit and onto a fatal trajectory. The rate of planetary destruction in those inner regions is likely orders of magnitude higher than out here in the quiet outskirts. This cosmic perspective forces a humbling realization. The stability we take for granted, the steady warmth of our sun, and the predictable rhythm of our seasons is an incredible statistical privilege. It implies a sobering possibility for the cosmos at large. While planets themselves may be common, even in hostile environments, the number of worlds that enjoy a long, uninterrupted period of tranquility necessary for complex life to arise might be drastically limited. A civilization evolving in a galaxy's core would face a constant existential threat, its potential cut short by a random gravitational nudge or a sudden, brilliant flash in the sky signaling a neighbor's doom. Our existence is therefore a double-sided coin. It demonstrates the robust potential for life in the universe while simultaneously highlighting its profound fragility. The same gravity that holds our world together and keeps us in a stable orbit around our star becomes an unstoppable shredder in the heart of a black hole. We are not just living in a universe that allows for life. We are living in a universe that has, thus far, spared us from being torn apart. This invisible ocean of dark matter could be the unseen director of the entire cosmic drama. While we cannot see it or touch it, dark matter makes up the vast majority of all matter in the universe, forming an immense, diffuse halo that envelops every galaxy, including our own. Its presence is felt only through its gravitational pull, a ghostly hand guiding the motions of stars and planets. In the chaotic core of a galaxy, this dark matter is thought to reach its highest density, creating a deep, invisible gravitational well around the supermassive black hole itself. An incoming planet feels this additional pull, a subtle but constant tug from the surrounding dark matter. This extra gravitational influence could be enough to nudge a world that was on a stable path onto a fatal one, effectively increasing the number of planets that fall victim to these events over cosmic time. The destruction we observe might be happening against a far denser and more influential backdrop than we ever realized. But how could we possibly detect the signature of something that emits no light? The violence of a tidal disruption might provide the key. Some theoretical models propose that the intense gravitational and magnetic fields near a black hole could act as a powerful particle accelerator. Dark matter particles drawn into this maelstrom could be slammed into one another with such force that they annihilate, transforming their mass into a flash of gamma rays or producing a shower of neutrinos, ghostly particles that can pass straight through planets. Detecting such a signal coinciding with a planetary disruption would be a monumental breakthrough, a direct glimpse into the nature of the universe's dominant but hidden matter. This connection remains speculative, a frontier of theoretical astrophysics, yet it perfectly illustrates how the study of one profound mystery, the violent end of worlds, is inextricably linked to another, the search for dark matter. Each brilliant flare from a dying planet does more than illuminate a black hole. It potentially illuminates the entire dark scaffolding of the cosmos. This paradox strikes at the very heart of our understanding of physics. When a planet is torn apart and its matter vanishes past the event horizon, what truly happens to the information that defined it? Every detail, from the precise arrangement of atoms in its core to the chemical signature of its ancient oceans, seems to be erased from our universe. This is the black hole information paradox, a profound puzzle formulated by Stephen Hawking. It reveals a fundamental conflict between our two most powerful theories of reality. On one hand, quantum mechanics, the rules governing the very small, states with absolute certainty that information can never be destroyed. It can be scrambled, hidden, or transformed, but it must persist. On the other hand, general relativity, our theory of gravity and the very large, dictates that anything crossing the event horizon is lost forever. The black hole consumes the planet, and according to classical physics, that should be the end of the story. The paradox deepens with Hawking's own discovery that black holes are not entirely black. They slowly evaporate over astronomical timescales, emitting a faint whisper of radiation. But this Hawking radiation is thermal, it is random and featureless. It appears to carry no information about what fell in. So when the black hole finally evaporates completely, all the information about that planet would have vanished from the universe, violating a cornerstone principle of quantum physics. This is not a minor technicality. It is a crisis that suggests our foundational laws are incomplete. How could the universe simply forget an entire world ever existed? Proposed solutions to this paradox are as mind-bending as the problem itself. One leading idea is the holographic principle. It suggests that all the information about the three-dimensional planet falling into the black hole is not lost inside, but is instead perfectly encoded on the two-dimensional surface of the event horizon. Like a cosmic DVD, the horizon stores a perfect, albeit incredibly scrambled, record of everything that fell in. This information is then slowly and chaotically released in the Hawking radiation over eons. Another, more violent proposal is the firewall hypothesis. It suggests that the event horizon is not a peaceful threshold but a blazing wall of energetic particles that instantly incinerates anything that touches it, preserving information by never letting it actually enter the black hole. While we cannot yet test these ideas with a telescope, the destruction of a planet provides the perfect thought experiment. The planet is a complex object, rich with information. Its demise a clear example of the potential for information loss. These theoretical battles over the fate of a consumed world force us to confront the fundamental nature of reality itself. Is information the most indestructible substance in the cosmos, or can gravity truly make it disappear? The death of a planet becomes more than a spectacular light show. It is a direct challenge to our understanding of the universe's most basic rules. The specific composition of a doomed planet dictates its final moments with brutal clarity. A low-density gas giant, a vast sphere of hydrogen and helium like Jupiter, presents a massive and fragile target. Its immense size is its greatest weakness. The tidal forces from the black hole can get a firm grip on its tenuous outer atmosphere from a tremendous distance, far beyond the point where a denser world would remain intact. The destruction would be a layered unraveling. The outer cloud decks would be peeled away first, stretched into a magnificent, shimmering veil of gas that glows with intense heat as it spirals inward. This process could continue for some time, stripping the planet down layer by layer, until only its compact, rocky core remains. That core would then face its own quick and violent end, spaghettified in a final, decisive moment. A terrestrial planet like Earth or Mercury tells a very different story. It is a solid ball of rock and metal held together by the powerful chemical bonds of its minerals. It does not unravel, it shatters. When the tidal forces exceed its gravitational binding energy, the entire world fractures catastrophically along global fault lines. Its crust, mantle, and core are all torn into a stream of molten and solid debris simultaneously, a rapid and total disintegration. From the distant icy reaches of a solar system, a frozen world would meet its fate. Composed of water, methane, and ammonia ices mixed with rock, its death would be explosively volatile. The sudden heating and pressure release from the tidal forces would cause these frozen gases to flash into vapor almost instantly. The planet would effectively explode from within, its ices transforming into a dense, complex cloud that rapidly feeds the growing accretion disk, enriching it with a unique chemical signature. This is the grim birth of a new scientific field, comparative planetology of the doomed. By carefully analyzing the light curve and spectrum of a tidal disruption flare, astronomers can perform a remote autopsy. A long, drawn-out brightening suggests the gradual stripping of a gas giant's atmosphere. A sharp, intense spike of light followed by strong spectral lines of silicon and iron points to the sudden shattering of a rocky world. The detection of water vapor or complex carbon molecules could be the ghostly echo of an icy planet's destruction. each type of planet, in its violent end, reveals the secrets of its internal structure and composition, secrets we could never learn by staring at it from across the void. The black hole's destructive power becomes an unlikely tool for discovery, a scalpel that dissects worlds too distant to ever see, telling us what they were made of just as they cease to exist. The entire life cycle of a planet's destruction operates on two different clocks, one for the outside universe and another for the world itself. From our distant vantage point, the entire event unfolds as a slow-motion cosmic bloom. The first signs of tidal distortion might appear weeks or months before the main disruption, as the planet begins its final, accelerating plunge. The brilliant peak of the flare, when the accretion disk shines at its brightest, could last for several more months, followed by a gradual fade over a year or more as the black hole consumes the last of the debris. This entire observable timeline, from first light to final dimming, is dictated by the slow, viscous drift of matter in the accretion disk and the sheer scale of the orbits around a supermassive black hole. Yet for an observer standing on the planet's surface, the reality would be terrifyingly different. The final act would be a blindingly fast catastrophe. Due to the intense gravitational time dilation near the black hole, your clock would tick infinitely slower compared to the outside universe. You would witness the sky tearing open and the ground ripping apart beneath your feet in a matter of seconds, a violent flash of heat and light before everything ended. The planet itself is shredded from a solid world to a stream of gas in a matter of hours, perhaps a few days at most, in the reference frame of the black hole. This stark difference in perceived time is not an illusion. It is a fundamental feature of Einstein's warped spacetime. The subsequent process, where the long stream of debris collides with itself and settles into the glowing accretion disk, operates on its own slower clock. This circularization phase is governed by the internal friction of the gas, a gradual bleeding of orbital energy that can take months. Then the final, slow spiral inward begins, a viscous timescale that dictates how long the flare will last. For astronomers, understanding this multi-stage timeline is absolutely critical. It tells them precisely when to point their most powerful instruments to capture the most revealing data. The early distortion phase offers clues about the planet's structure. The peak of the flare reveals the composition of its guts. The slow fade charts the black hole's feeding habits. Each phase of this violent rhythm provides a different piece of the puzzle, a fleeting chance to read the story of a world's end written in light and time. The hunt for these elusive giants focuses on the very light they produce. A disruption flare from an intermediate mass black hole would be a perfect cosmic intermediary. It would not be the brief, faint flicker of a small black hole born from a dying star, nor the brilliant, year-long blaze of a supermassive monster. Its light curve would be a clear middle ground, shining for weeks or months with a distinct and measurable brightness. Spotting this specific signature is like finding a missing link in the evolutionary chain of black holes. For decades, astronomers have searched for these intermediate beasts in their suspected hiding places, the dense globular clusters that orbit galaxies and the small, faint dwarf galaxies. These environments are quieter and less chaotic than galactic cores, making them ideal nurseries for a growing black hole. Yet, without a feeding event, an intermediate mass black hole is nearly invisible, a silent phantom in the dark. This is why a planetary or stellar disruption is such a precious opportunity. The sudden, violent death of a passing object acts as a perfect flare, illuminating the hidden predator and revealing its mass through the very nature of the explosion it creates. Each candidate event is scrutinized with immense care. The duration of the flare, the peak of its luminosity, and the temperature of its accretion disk all provide independent clues that point to the mass of the central object. When all these clues align to suggest a mass of thousands, not millions, of suns, it is a powerful indication that an intermediate mass black hole has been found. The implications of such a discovery are profound. Do supermassive black holes at the centers of galaxies grow from these smaller seeds, gorging on gas and stars over billions of years, or do they form through some other, more exotic process? Finding a population of intermediate mass black holes would provide critical evidence, showing us the missing middle stage in the life cycle of the universe's most mysterious objects. This transforms the tragic end of a planet or star into a crucial scientific instrument. Its destruction becomes the key that unlocks the door to understanding how the largest structures in the cosmos came to be. The superheated debris from a shattered planet is far more than just a cloud of hot gas. It is a plasma, a seething ocean of charged particles where electrons are stripped from their atomic nuclei, creating a substance that can conduct electricity and generate its own magnetic fields. This invisible force of magnetism becomes a powerful and often violent actor in the final act of a world's destruction. As the chaotic stream of planetary material wraps around the black hole, any faint, primordial magnetic field carried by the planet is caught in the whirlpool. The incredible shear forces with inner parts of the stream orbiting vastly faster than the outer parts stretch and amplify these magnetic field lines, weaving them into an intensely tangled and powerful web. This magnetized plasma can no longer behave like a simple fluid. It can channel immense energies, launching narrow, focused jets of material that scream away from the black hole's poles at nearly the speed of light. In some of the most dramatic tidal disruption events we observe, it is these brilliant jets, powered by the black hole's spin and guided by magnetic fields, that we see first, piercing through the darkness of intergalactic space. But the role of magnetism is not only about spectacular outflows. It is also the hidden engine of the accretion disk itself. For the disk to feed the black hole, the gas must lose its orbital energy and spiral inward. The mechanism for this is viscosity, a kind of internal friction. In the vacuum of space, ordinary friction does not exist. Instead, the tangle of magnetic fields provides the necessary grip. The fields create turbulence, a magnetic friction that causes the particles in the disk to rub against each other, transferring angular momentum outward. This allows the inner material to drift inexorably toward the event horizon. In fact, without these magnetic forces, the debris might never settle into an efficient feeding disk, and the brilliant flare of light we rely on for detection might be far dimmer. The entire system becomes a complex dance between three powerful forces: the overwhelming pull of gravity, the fluid motion of the superheated gas, and the structuring influence of magnetism. This trio, described by the challenging laws of magnetohydrodynamics, makes simulating these events one of the most difficult tasks in all of computational astrophysics. How can we possibly peer into this magnetized maelstrom? The light itself holds a clue. As photons travel through the magnetized plasma, their electromagnetic waves can become aligned or polarized. By carefully measuring this polarization, astronomers can work backwards, deducing the strength and geometry of the magnetic fields near the black hole. It is a subtle fingerprint left on the very radiation screaming from the inferno. So, while gravity is the undeniable executioner, it is magnetism that often directs the orchestra, shaping the final, luminous cry of a world torn apart. We are about to witness a golden age for these cosmic cataclysms. The tools we use to observe the sky are undergoing a revolution, promising to transform tidal disruption events from rare curiosities into a rich field of statistical study. Leading this charge is the Vera C, Rubin Observatory, a facility being built in Chile with an almost unimaginable scale of ambition. Its massive mirror and enormous digital camera, the largest ever built, will act as a tireless sentinel. It will photograph the entire visible sky not once a year, but every single few nights. This relentless pace will uncover a fire hose of cosmic change, spotting thousands of fleeting flashes. Among them will be countless new tidal disruption events, many of which would have slipped through our nets just a few years ago. It will find them not only in nearby galaxies, but in the farthest, earliest reaches of the universe, giving us our first true census of these violent encounters across cosmic time. But finding the flash is only the beginning. Once a new flare is spotted, the James Webb Space Telescope will bring its immense infrared power to bear. Its ability to see through cosmic dust is a game-changer. Many galactic centers are shrouded in thick clouds, hiding their central black holes from optical view. Webb can peer directly through these veils, studying the chemical composition of the shredded debris with a precision we have never before possessed. It will be able to identify not just the obvious elements, but trace molecules and compounds, reading the detailed life story of the destroyed world from its final, glowing remains. To understand the true inferno at the heart of these events, we must look to the highest energies. Future X-ray observatories with unprecedented sensitivity will stare directly into the maelstrom. They will probe the innermost regions of the accretion disk, where matter is heated to tens of millions of degrees just before it vanishes. This data will reveal the extreme physics at the very precipice of the event horizon, showing us how space, time, and matter behave under conditions impossible to replicate anywhere else. The most profound shift, however, will come from listening to the universe in entirely new ways. The era of multi-messenger astronomy is here. We will no longer rely solely on light. The future space-based Gravitational Wave Observatory, LISA, is designed to hear the low-frequency hum of a planet's final spiraling orbits around a supermassive black hole. Detecting the same event in both light and gravitational waves would be like watching a silent film suddenly gain a perfect soundtrack. The light shows us the color and heat, while the gravitational waves give us an exact measurement of the masses and the orbital dynamics, confirming our models with stunning accuracy. We might even detect a shower of neutrinos, ghostly particles that fly straight out of the heart of the disruption, offering a third, independent messenger from the catastrophe. With this incoming flood of data, a new kind of explorer will become essential, the citizen scientist. Online projects will allow anyone with curiosity to help classify the strange and wonderful things these new telescopes find, turning the public into partners in discovery. This collective effort will allow us to move beyond individual stories. We will begin to understand tidal disruption events as a population. How often do they really happen in different types of galaxies? What is the full variety of worlds that meet this fate? And what role does this violent consumption play in the long-term evolution of galaxies, perhaps even regulating the growth of their central black holes? The next decade will not just add more data points to a chart. It will fundamentally rewrite our understanding of the chaotic, dynamic, and beautiful violence that shapes our universe. This cosmic violence forces a humbling perspective on our own place in the universe. We are built from the very elements forged in stellar explosions and scattered by cosmic cataclysms, yet our existence depends entirely on being spared from that same chaos. The destruction of a world by a black hole is a stark reminder of impermanence on the grandest scale. No planet, no star, no structure is truly permanent. Everything is subject to the relentless laws of physics, laws that can both build and obliterate with impartial force. A planet that may have nurtured life for billions of years can be erased in an instant, its potential snuffed out by a random gravitational nudge. This reality forces us to confront a profound question. In a universe so vast and so violent, is life an incredibly rare and fragile spark, a fleeting anomaly in the darkness? The sheer power of these events suggests that the cosmic environment is, for the most part, hostile to the delicate, long-term stability that complex life requires. Our own civilization exists only because our world has, thus far, been lucky. We orbit in a quiet stellar neighborhood, far from the galactic core's gravitational pinball machine. This safety is not a given, it is a statistical privilege. Yet, there is a powerful counterpoint to this existential dread. Our ability to witness these events, to understand the physics that tears a world apart, and to predict its brilliant final flare is a triumph of human curiosity. We are not just passive subjects of cosmic forces. We are the universe become self-aware, looking back at its own violence and seeking to comprehend it. We can find a strange beauty in the destructive process itself, in the elegant physics that governs a planet's demise. This unique position as conscious observers bridges the gap between raw physical process and deep human inquiry. The study of a world's end is not a morbid pursuit. It is a search for context, a way to understand the full life cycle of cosmic matter, from its creation in stars to its consumption by black holes. It connects the fate of distant planets directly to our own search for meaning, reminding us that our brief, precious existence is set against a backdrop of both magnificent creation and terrifying